Okay, so lastly, why are we even talking about chirality? And the reason is because life is chiral. Our DNA is chiral, and that's how it works. The sugars that we eat, the carbohydrates we're talking about, they're chiral. And if you change one chiral center, it changes the sugar and it changes how it interacts in your body. Amino acids and enzymes, so proteins, they're all chiral. And it's just how life works. So nucleotides, which are the parts that make up our DNA, are also chiral, and that's why we get that helicity structure in one direction every single time. So, for example, enzymes here. Enzymes are a fancy word, but it's a I wrote enzymes that act as catalysts. They're proteins that act as catalysts, and they're in all of the cells of our bodies. It's how pretty much everything in our body really works. And if you see in these molecules, so this is kind of like a cartoonish version of an enzyme. It kind of has a hole, a pocket of reactivity. So chiral receptor sites on an enzyme surface. So the surface of the enzyme will have a special pocket that only interacts with particular molecules. And these two molecules are enantiomers of each other, kind of with shapes, right? But they're enantiomers of each other, but the enzyme will react with one enantiomer, but not the other. Enzymes are very much so recognizing enantiomers in our bodies. Additionally, there could be differences in taste, for example. So these two molecules here are enantiomers of each other. They are chiral molecules. L-carvone is spearmint flavoring, or the kind of essential oil of spearmint. Whereas if you just switch this one chiral center to the enantiomer, then you have caraway. So caraway seeds, it's a completely different taste. Doesn't taste like mint at all, right? So just changing that one enantiomer changes how we taste those molecules as well. And then the last one, which is really important, is talking about drug activity based on chirality. So this first molecule here is ibuprofen, and this atom, or this carbon, is the chiral carbon in ibuprofen. And so simply by selling ibuprofen as a single enantiomer, it reduces the dosage required in your body to have the effect, because your body only interacts with one enantiomer. It increases the activity then, because your body's not trying to fight getting rid of the wrong enantiomer. And it also decreases side effects. So the other enantiomer causes different effects in your body. So selling ibuprofen as a single enantiomer overall has health benefits to that drug, or when you use that drug. And then a historically monumental drug in terms of actually just changing how pharmaceutical companies work. Sorry, this light turns off. There we go. Is thalidomide. I think it's thalidomide, sorry, is how you pronounce it. But so this is a drug molecule that was, I believe it was 1958, that it was approved to be used as a variety of different things, specifically a sedative. So it just kind of helped in general reduce like pain and everything like that. And it had been originally put on market for a variety of different things. It's kind of like a heal-all molecule. And what they were selling, they were selling the mix of the enantiomers, which is called racemic, but they were selling both versions of it in one bottle. And they had done a bunch of tests on it, made sure that it was healthy and safe for people to take. And it turns out it was for most of the population. However, they also sold this as a morning sickness drug for women who were pregnant. And where this became an issue is that the D-enantiomer was definitely effective at preventing morning sickness. However, the L-enantiomer has severe side effects in growing fetuses. Specifically, it's called a pterogen, which decreases blood vessel growth in fetuses. So women who took this as a drug to help their morning sickness had babies with severe birth defects. So the most common birth defect and what it's most known for is there were a large number of babies who were born without some of their limbs. There's also some, I read about some like eye deficiencies and stuff like that, but the most common was that as the fetus was growing, the blood vessels couldn't grow because of the pterogen properties. So in order to help the fetus survive, the nature of it naturally just made it so that their limbs didn't grow, because then they couldn't get blood to those limbs. And so in 1961, this molecule was taken off of the market as a effective drug, but in all of the other uses for it, it was completely fine because it didn't affect the growing of something, right? If you took it for something else and you weren't pregnant, it was fine because your blood vessels had already grown. But a fetus, it was a really bad situation. So I just read the article on it again to refresh myself, said that there were approximately 10,000 women who were pregnant who took this drug in the about 2-year time span that it was out on market before they caught this and took it off market. Or I think it was 3 years total it was on market. But there were about 10,000 women who took this, and around 4,000 or 60% of those fetuses even survived. 40% did not survive and were either stillbirths or miscarriages because of this molecule. And the other 60% are so there's approximately 6,000 people who are born without limbs because of this molecule used as a drug. So to me personally, at least a little backstory for me, is both of my parents were born in 1960, which is right, like the second year, right as they kind of were catching it. I think it was 1961 that this was banned. And so my parents could have been born without limbs. And if they were born without limbs, maybe I wouldn't even be here. So it's kind of crazy. It's just my parents this could have happened to. It's not like something that happened way, way, way long time ago, but it was within our lifetimes or our parents' generation that this happened. And this is actually the molecule that really upped the safety of drugs. So for example, the COVID vaccine that's coming out right now, and there's a lot of debate over whether it's been tested enough. A lot of those tests and those the frighteningness of that's not a word, but you know what I mean, is because of things like these molecules that got passed but without thorough testing. So testing protocols throughout the world changed because of these, specifically this drug and this tragedy that happened. But enough of me talking. That's a fun story that a lot of organic chemists like talking about. Not necessarily fun story, I guess, but it's a very informative story and it touches a lot of people's hearts. So it's really important. Chirality in general is really important, and especially in drug molecules. And yeah, it's important in everything. So that's why we're studying it.